Okay, yeah, so we're gonna start on topic 15. Okay, so if you come to our course website, okay, so today we hope to cover decisions and uncertainty, and if we get extra time, we can start on number 16 as well, okay? But you will see that starting from here, especially from last week, if you remember, we talked about assessing models, right? We're saying that model is really, any model is a set of assumptions, okay? And then we're coming up with method of how to simulate, right, data under what the model is saying, and then use that to check against what we observe in the sample. Okay, so we talk about like the jury selection example, Mendel's heredity model example, and then I remember, I believe Jason talked about how to compare distributions, right? And then in the Slack channel, I think we had a discussion, quick discussion earlier this week also about what is the total variation difference is doing, and things like that. So today we're trying to synthesize all of them, okay, with a larger example that involves how we can actually simulate the data under what the model is making the assumption for. So we'll revisit some of the concepts from last week as well, but at the same time, we're going to talk about some new stuff, okay? So we'll get started, okay? So the first part here is we titled this topic as decision uncertainty, mostly because, well, before we talk about how you're able to come up with simulation approach, right, to figure out how you can simulate data under what the model is saying. And then, of course, based on that, we're going to say that, oh, the model seems consistent, right, with the observed data, or does not seem consistent. So we were using, I guess, overall pretty vague language back then, saying that, well, consistent, what is not. And today in this topic, we're going to talk a little bit more about, well, what do we really mean by that? How we can make decision once we have a set of simulated statistic, right? And then we compare against the observed. How extreme is extreme? How inconsistent is inconsistent? Okay, so we're going to talk about based on what we're going to make those decisions. And then you will see as soon as we start doing that, whenever you make decisions based on any rule, it's possible that you make a mistake. Okay, and then we're trying to capture that in terms of what we mean by uncertainty. Okay, because you could make mistake. Any kind of rule will have rooms for you to make mistake, right? But then we definitely want to make sure that we will minimize that kind of mistake as much as we can, so we can have a really robust test that we're talking about. Okay, so this is like the overview of today. And to start it off, we're gonna look at what we have been doing, and then see what we can carry on what we're doing. Okay, so from last week, we were choosing, right, between 2 viewpoints of the world, right, based on the data in the sample. In particular, in the jury selection, I think Alameda counted example, we're talking about the first viewpoint, right, where we think the jury selection is a random sample from the population, right, and then the other one is that they're not. Okay, so those are the two viewpoints, and we are trying to choose between them, which one is more likely given what we see in the data. Okay, and then last week we also talked about it's not always clear whether the data is consistent with one view or the other. Sometimes it's very extreme. I remember that example about the jury selection in 1965, the one that I talked about, if you remember, like eight African-American men on a 100-person jury, where the population breakdown of that race or ethnicity is 26%, right? So that was something pretty extreme that when we simulate the data, we can see that, well, it is pretty clear that it's not consistent, okay? But sometimes it might be much harder to make the decision, okay? So that's why we're trying to talk about, like, based on what rules we're gonna make the decision and how we're gonna go about doing that, okay? And so this is what we have so far, okay? So to start off, we're gonna again start with some terminology. So let's take the step one by one over here, okay, just to make sure that we're all on the same page, okay? All right, so here, the hypothesis, okay, so the hypothesis that we're gonna start talking about here will be pretty much the same thing as what we were talking about before, the different viewpoints, okay? And typically we come up with two, okay? One of them is what we're going to call like the null hypothesis. Okay, the other one going to be what we call the alternative. Okay, but I want to highlight that the hypothesis, we are using the term here, nothing fancy, is the viewpoints of how the data are generated that people can come up with. Okay, for the jury selection example, the two viewpoints, like what we're reviewing just now, is the first one, right, is that no, there's no gender discrimination, there's no racial discrimination, right? Like it's a random selection. out of the population, right? That's the first viewpoint. The other one is that it's not, okay? And so when we have when we can come up with two hypotheses or viewpoints over here, we're gonna try to come up with a test to figure out which one is more likely under the data, okay? So we call those two viewpoints hypothesis, okay? And then the test that we're gonna do is to pick the hypothesis that is better supported by the observed data. Okay, so as we're doing now, as you could see as well as recall what we did so far, is that we need to figure out a way, right, to simulate the data, right? Simulate data based on maybe one of the hypotheses, okay? And then try to figure out how the simulated data looks compared to the observed data. And then that's how we come up to the point of how we can do the comparison and make decision. Okay, so terminology wise here, we're introducing the first new terminology, hypothesis. Okay, they're really just the viewpoints of how data are generated. In the jury selection example, we talk about one hypothesis or one viewpoint about it's a random selection, there's no discrimination, right? The other one is it's not a random selection, there's some discrimination. Okay, so keep those in mind. We come up with two, and then we're going to try to simulate data under one of the hypotheses, as you can see, as we're always going to be doing, and then that will be what we're going to compare to the observed data. Okay, so the method, okay, only works if we can simulate data under one of the hypotheses. Okay, so if you recall what we did, I believe in any of the jury selection example or in the Mendel example, we have to simulate data under one hypothesis. Okay, and then we're saying that for the jury selection example, if you recall, we're going to simulate the data under the hypothesis that it is a random selection, right? So for that example of 26% of Black men in that community, the way that we're doing the simulation, if you remember, is trying to simulate a large number of samples, right? Under the assumption that 26% is the percentage. So we're looking at the number out of, like, say, or we're interested, I guess, in the number of Black men going to be selected on a 100-person jury, right? Under the assumption that it's a 26% from the population. Okay, so as you can see, the hypothesis will have to be, one of them has to be made in a way that we can simulate data under that. And that is what we usually call as the null hypothesis. Okay, null hypothesis, based on the term, you can take it as nothing is going on. Okay, nothing is fishy or anything. It's the status quo. That's what we call usually as the null hypothesis. Okay, so in our framework here, okay, we're gonna determine or define the null hypothesis as a well-defined chance model about how the data were generated. Okay, and in particular, we need to generate the data under this assumption. Okay, and when we say that, we're gonna say we can simulate data under the assumptions of this model, which is also saying that under the null hypothesis. Okay, so to bring back again, using the jury selection example, our null hypothesis, it is that it is a random selection. Okay, it is a random sample. So the way that we're able to generate or simulate data under the null hypothesis will be that it's 26% in the population. So I'm going to generate, right, number of people out of that 100-person jury based on that null hypothesis of 26%. Okay? So that's the null hypothesis. And as we recall, we have two hypotheses, right? One is the null, the other one will be what we call the alternative. And that is a different view about the origin of the data or how the data is generated. And of course, there could be different ways to term the alternative hypothesis, even if you have the same null hypothesis. For example, let's just say we have a test. We have a data set that we want to test about, say, so suppose I collect information from you all, asking about how many hours per night you get to sleep, okay? And let's just say I get from each of you like 21 data points, okay? And then let's just say that I'm curious about whether people are sleeping, like say, enough. Okay, like enough meaning that, let's just say whatever the study tells me that on average people better sleep 8 hours per night. Okay, so then for that kind of test that I will be doing, then the null hypothesis will be that the average is 8. Okay, and then the alternative hypothesis, if I frame my research question as whether people get enough sleep or not, right? Then my alternative hypothesis will be that whether people are, I guess, the average is less than 8. Okay, because I'm curious about like whether it's sufficient or not. And I determine 8 as the sufficient number. Okay, so that will be like one way to set up my alternative hypothesis, right? And it could also be that, okay, instead of thinking about whether people get sufficient or not, I'm just curious about whether people get 8 hours or not, okay? And then for that kind of research question, my null hypothesis will still be the mean is 8, okay? But then the alternative will just be the mean is not 8. Okay, so one is that the mean is smaller than 8, depending on how you phrase your research question. Okay, the other one will be, well, it's not 8, like does not equal to 8. So those are examples of like different hypotheses you're able to set up. But at the end of the day, I want to use this example to highlight that the null hypothesis is always sort of like the status quo. Okay, you are always, you have to keep in mind that the null hypothesis needs to be one of the two that you can generate data based on. Okay, and then that's what you're going to set as the null hypothesis. And the alternative hypothesis will be depending on how you're going to frame your research question, just like the sleeping example that I was talking about. Okay, but for us, we're going to be very specific for every example that we walk through. Okay, like what is the null, what is the alternative, and from there we can start doing our test. All right, I guess for this discussion question, I was talking a lot already, so maybe I will skip this one. This is the null and the alternative hypothesis in the Alameda County jury selection example from last week. Okay, so null hypothesis, like we were saying earlier, is that it is a random selection, okay? And then the alternative will be that they're not, okay, based on the stuff that we talked about. All right, so any quick questions here, like the null and the alternative, how to set it up, what is the right one to use, what's the difference between those two? Anything general? Okay, like I said, the hypotheses are very much representing the viewpoints that we're talking about before. Okay, but instead of before, we're being a little less formal. Now we're formally defining those for hypothesis, and then we are creating the entire procedure of how to do the hypothesis testing that we're talking about. All right, so good with that. If we are able to come up with two hypotheses, one is the null, the status quo. Okay, the other one is the alternative, that is different from the null, and depending on how you phrase it, you can do it like different ways that we're talking about. And now the next step, okay, is the test statistic. Okay, so we've been doing this a little bit in all of the previous examples already, the jury selection, Mendel's model, and stuff like that. So let's formally define it and then also discuss it in the context. Okay, so the statistic, okay, is the one that we're going to choose to simulate. Okay, and then we will have to be based on it to choose between the two hypotheses. Okay, this sounds a little bit vague at this point, but let's go over the terminology first and then come back to the jury selection example. Okay. So questions, okay, before choosing the statistic. And the first one is, what values of the statistic would make us lean towards the null hypothesis? Okay, so like, remember, whatever statistic that you're gonna decide to do, right, will be helping us, needs to be helping us to make the decision. Okay, so when you choose the statistic, you better choose a one that, well, whatever, like say, values, and like what values make us lean towards the alternative. And then we want to make sure that maybe falling, like the statistic falling into a certain range can tell us a little bit more about which one we're gonna choose or which one we're gonna prefer between the two. Okay, and I would just say that preferably the answer should be just high. Okay, try to avoid like using like both high and low in terms of what values will make us lean towards the alternative, because it's going to be a little bit harder for us to make the decision. Okay, so let me check quickly. I think there is a chat question. Okay, so the question, I'm gonna I'm gonna read the question. Are we going to be looking at ways to avoid p-hacking and harking while using the NHST model? Okay, so I guess some of the terms we probably need some clarification. So like if you can type a little bit more about the harking and the NHST model, please go ahead and keep doing that. I can return to those a little bit later. But then the first part of the question I will try to answer here. So the question is, are we going to be looking at ways to avoid p-hacking? Okay, so some of you, I don't know if all, have heard about the term p-hacking. And we will see that even more so because later we're going to define what a p-value is. So you will see that we're going to define what a p-value is. And then p-value is pretty much like the decision criteria when people are deciding which hypothesis to reject or not. Okay. And I would just say early on now, and we can revisit this concept later, is that because in a lot of scientific studies, okay, in social sciences as well, actually, that people know that, well, in order to have some, like, say, very strong conclusion to make, you will have to pass, like, say, use a particular p-value, and then using a particular threshold, and then if your p-value falls below a certain point, you're able to make those kind of strong statements. Okay, if not, then it's almost like the study is go wasted. Okay, like nothing is really conclusive coming out of it, and then what we're going to do about it. So the question that was asked just now is that there's a phenomenon people call as p-hacking. It's almost like, okay, I'm going to do my study, and then as long as I'm able to, like, say, make a strong conclusion or significant result, maybe you have heard about those terms before, then I'm happy, and then I will report whatever I have. But if I don't, maybe that involves, okay, maybe I start to look at a different research question with the same data set, or maybe I can just keep collecting more data until my test becomes significant. Okay, so those are issues actually right now a lot, I would say, going on in natural sciences as well as social sciences. And so we will talk, I guess, to some degree about, like, in terms of dealing with it, I guess people just need to be honest, And a lot of times I would say that the insignificant test is also telling us something, like, say, maybe that would just tell us that, okay, maybe this kind of research is not, I wouldn't say not important, but not significant. So you can actually tell the future researchers, knowing that this is maybe not worth your effort, putting more effort into answering this kind of question, right? Like my test already shows, or my research shows that. But in terms of, I guess, actually to make it happen, and then people are following those rules, I guess it's probably going back to the core of why people are doing science in the first place, right? And then why you're thinking about doing all of this. So we'll try to address some of this. Okay, so I guess that's my quick answer to that question. But again, I think maybe not everybody knows about this kind of concept. So I will try to revisit a little bit more, and then tell you all a little bit more. Yeah, so thanks for the question and the follow-up. I will come back to this, especially after we talk about the p-value, okay? Because right now I'm worried about, everybody knows what we're talking about right now, but at the end of the day, you will see that there are issues going on in how science is being done, especially how statistics is being used in scientific studies, okay? And then I think for us, it's very important to keep in mind, I guess, for the very least, for all of you doing your final project, for example, if you come up with something that is not like very strong conclusion you can make, be it. Like, we won't say that is wrong. It is what it is, right? But you want to make sure that you have done all of the procedure correctly. And if that is the case, then if it's not a strong conclusion about certain research question you want to study about, that's fine. And I think we're all going to take it. I think we will try to definitely avoid p-hacking in that particular sense, and then follow what we understand is correct, and then go from there. Okay. All right, I will continue for a little bit, and then once we get to the definition of p-value, we can spend some more time talking about all of this, okay? All right, so coming back to here, the test statistic, okay? So again, we are posting these questions for you, especially like later on, you might be the person to choose the statistic that you want to do, okay? Remembering the Mendel model example, I think from last week, that there's multiple statistics that you can return, right? Like, say, the difference between whatever the statistic that you compute with 75, or like the that value minus 75, or like to the absolute value of the 75, things like that. So what we're trying to show here is that we want to design statistic, right, that we're able to show us or help us to understand what values of it will make us lean towards more of the null, and what are the other values will make us lean towards more of the alternative, okay? And then we better have a pretty easy breakdown of those two. And that's why we're saying over here, the answer should be just high. Try to avoid both high and low, because then that will just make the things a little bit more complicated. Okay, so with all of this in mind, okay, let me put you in a breakout room really quick. Okay, I wanted to revisit the test statistic in the Alameda County jury selection example from last week. Okay, I know this probably require you to go to our website and then go to topic 14 just to have a quick look. at what we did, but I think this will be a good effort and time well spent just to bring everybody on the same page and then think about what we really mean by test statistic. And then I want you to refresh your memory and think about why back in that example. So this is that example. And I will give you the time to go to the breakout room to take your time to think through and then talk about it. And then when we come back, we're going to resume and then talk about it as a class. Okay, so let me stop share here and also okay, welcome back. I think pretty much everybody's back. I'm sharing the screen one more time here, and I also have the topic 14 slides next to me, so next to this. So whoever wants to maybe volunteer, talk about what your group has talked about, and then what was the test statistic and why we chose that, that would be greatly appreciated so we can move along. Okay, anybody?
Yeah, so my group thought that it was the percentage of Black men in the county. And then basically you're going to see if the percentage of Black men on the jury is representative of that.
Yeah, indeed. Yeah, so I think, let's see. So the generic, okay, I guess I should, yeah, actually give me a second. I was suggesting everybody to go ahead and look at the demo, but then how about I would just open the demo really quick. Okay, so instead of running it, I will just say that I think, okay, I can run it really quick anyway. All right, let me do that. Okay, so this was, if you remember what that demo was, right? So other than Black, we have Asian, Latino, white, and other. Okay, so we have 5 different categories over here. And we made a table, if you remember, okay, where we have one column of the percentages of the eligible. Okay, that's what in the population. Okay, and then that was what we're gonna, like say, if we were to sample anything, it's gonna be from that kind of percentage breakdown. And then we also have the percentages in the panel. Okay, so what Xiao was telling us earlier is that, yes, we're gonna look at the distance, right, between the percentages of, I guess, not only Black in this case, we're gonna look at the distance of the eligible compared to the panel, the actual panel of all of the different categories, right? And then that will tell us like sort of like the distance between these 2 categorical distributions. And I would just also add that later on, we also talk about how we're able to use this total variation difference distance, if you remember this terminology, right? What we did for the categorical 2 categorical distribution is that for each category, we'll compute the distance. We take the absolute value of each distance, and then we take the sum and then divide the sum by 2. Okay, so that is when we say distance, don't forget it's absolute value. Okay, that's what distance should be non-negative. Okay, so we take the difference pretty much in Python, we take the absolute value of that and then take the sum and then divide it by 2. Okay, so those are what we mean by, I guess, the total variation distance, right? We use as a statistic. And I think the reason, okay, so maybe we can talk about that really quick as well, is that the reason why we choose that in particular is that we want to evaluate, right, how far these 2 distributions are. Okay, and in particular, we know that for each category, we have the eligible percentage, right? We also have the observed percentage, right? And then we know that the eligible is, in our new terminology now, should be the null hypothesis, right? Like that is the status quo, right? If it's indeed a random selection, it should be pretty close, right, to this eligible percentage breakdown, okay? And then what we're curious about right now is that, well, what we observe in the panels is this new set of 5 percentages, how close are they, right, to the eligible percentages? And then that distance can tell us how far away it is from the null hypothesis. Okay, so this is, like I said, hopefully a reasonable and sense-making example of what we mean here about the test statistic. Okay, we really want to pick, let me come back to here. Okay, we really want to pick something that we are able to use to make decision, right? In particular, we want to come up with statistic that some of the value is going to tell us that it will be leaning towards more of the null, and then the other set of the values is going to help us to lean towards the alternative. Okay, for that total variation distance example, that test statistic, I guess in general, the smaller that value is, the more evidence, right, for the null hypothesis. Okay, because the smaller the distance, the eligible percentages will be closer, like I should say, the panels, the actual observed percentages will be closer to what we expect to see if it's indeed under the null hypothesis. So small TVD will tell us more, will give us more evidence for the null, and then larger values of that SVD gonna give us more evidence for the alternative. Okay, so these are an example, and we'll see even more coming up. In fact, I think all of the hypothesis testing, as you can see now, is that we have to come up with a test, the two hypotheses first, and then we have to design and pick a test statistic that makes sense in our setting. Okay. Okay, so that's the second step, I guess, of doing hypothesis. The third one over here now, we have done this already, but I would just want to put it more formally in the procedure, is prediction under the null hypothesis. Okay, so this is what we mean by we are going to simulate data, okay, under the assumption of the null hypothesis. And then we're going to do that for a large number of times. Remember, we come up with histogram and then figure out how the observed data or the observed statistic compared to the simulated statistics, and we're going to use that to make decisions. Okay, so the procedure goes this way, just to, I guess, almost like a review for everyone here, hopefully, is that we're going to simulate the test statistic under the null hypothesis. We're going to draw the histogram of the simulated values. Okay, so again, you have to pick a test statistic in the first place, right? And then you need to figure out, how am I going to simulate it under the null hypothesis? Okay, so we're going to walk through an example soon, but just to keep you in mind, keep that in mind. This is the procedure that we need to do. And then once we get a large number of simulated values, we can draw a histogram. Okay, so that's what we mean. And this histogram, okay, going to display, so look at the highlighted here, that just to get the term right, okay, it is because it's simulated, okay, so it's going to be an empirical distribution, okay, and it is the simulated value is the test statistic, so it is the empirical distribution of the statistic. And moreover, we highlight here that it is the empirical distribution of the statistic under the null hypothesis. Okay, the reason is because the simulated data itself, right? We simulate a data set under the null, and then we compute the test statistic, right? So the statistic that we're showing, the histogram we're showing over here, it is about the statistic under the null, okay? But in particular, it's the empirical distribution of the statistic because it's based on the simulation, okay? And if you recall some of the terminologies we covered in the past, that for the statistic, right, we talk about the sampling distribution, right? Or like the probability distribution, that is what it should be in theory. Okay, but like we're saying, a lot of times it might not be easy to get that theoretical result. So we're rely on simulation-based approach. And as soon as we're doing simulation, we call all of the stuff as empirical. Okay, so that's why here, just to highlight one more time, the histogram that we're able to draw is the empirical distribution of the statistic under the null hypothesis. Okay, so keep this in mind. Okay, and then what we're going to take it as a prediction about the statistic made by the null hypothesis. Okay, so again, we simulate the data, calculate the statistic under the null hypothesis. So whatever the prediction we're making is based on that the null hypothesis is true. Okay, so that's what exactly the histogram is about. And if you recall the histograms that we have generated before, that is exactly what we're doing. And then we're going to compare it, right? We're going to have a histogram and then think about the observed value and then figure out where it stays. Okay, again, this prediction, it shows all the likely values of the statistic. Okay, not all of the possible values, but the likely values because it's simulated. Okay, it's possible that some value you never simulated. But overall, if you simulate large enough times, you're gonna pretty much cover most of these. So we call it all the likelihood values of the statistic, okay? And also how likely they are, okay, if the null hypothesis is true. So we highlighted again here is because this prediction distribution that we're getting over here is under the assumption that the null is true. Okay, so how likely they are, again, if you remember histogram, right? If we have the same bin width, right? So the height gives us a sense of how likely it is at each bin, right? So that's why that histogram not only tells us, like the bins are telling us the possible values, right? Or the likely values of the statistic, and then how tall each bin is in the histogram is telling us how likely each value is, okay? And then that overall can help us evaluate our hypothesis, okay? Lastly, the probability is approximate. We're talking about it. That's why we call it empirical distribution, okay? Because we cannot generate all of the possible random samples. But if we do it large enough times, okay, as we know by now, the law of averages, right? So we should be able to give a pretty good approximation of the theoretical results, and that's what we're doing, okay? So this is our third step, okay? So first step, come up with two hypotheses, okay? One is the null, the other one is the alternative. Second step is you have to pick a test statistic that you want to do, okay? Third step is you want to make a prediction under the null hypothesis. In practice, what that means is that we're doing a large number of simulations. Each time we simulate a new data set under the null hypothesis, we compute the test statistic, and then we draw the histogram. Okay, so these are the three steps so far, okay? Last step is how to make a conclusion of the test, okay? We were already saying earlier, like, if it's consistent with the observed data, then what we're going to do. If it's not, what we're going to do. So now formally, we're going to say that how to resolve the choice between the null and the alternative hypothesis is how we are actually making the conclusion here. Okay, so we compare, right? We compare the observed test statistic from the data and the histogram that we're able to generate. And again, the histogram is the empirical distribution of the statistic under the null hypothesis. If the observed value is not consistent, meaning that like it's far away from the bulk of the distribution or it's in the tail, right? It's very unlikely to happen. That's what we mean. If the null is true, then the test is going to favor the alternative and we're going to reject the null hypothesis. So let's imagine a histogram in our head really quick, okay? That we know that that histogram is telling us how likely each possible values are, right? And then also like listing all of the most likely the possible values out there, okay? And then now comes along, right? Like our observed statistic is here. Let's just say it's here, okay? If it's very much in the middle of the histogram, okay, then what that tells us is that, well, if the null is true, it's very likely, right, to simulate something like our observed data. But if it's far away, like if it's not in the histogram at all, that's where I think the jury selection example, the first jury selection example that we talked about before, about 8 and 26%, that pretty much tells us that it's not a random sample. Like we're going to reject the null hypothesis, okay? But sometimes the observed data might be somewhere in the histogram, okay? If it's not in the middle, if it's in the middle, great. We know that it's consistent, okay? But sometimes it might be in the tail. So how far in the tail do we determine is unlikely? Okay, so that's what we're going to talk about soon as well, how we're going to make the decision. But regardless, the general approach over here, as you can see now, is that once we get that histogram, right, we're going to compare it against our observed data. And the observed data could be inconsistent with the distribution, then we're going to reject it. If it's not, if it is consistent, then we do not reject the null hypothesis. So we're favoring the null hypothesis. Okay, so pretty much the general approach here is that we are simulating a large number of test statistics under the null hypothesis, meaning that we assume that the null hypothesis is true. I want to know how likely my test statistic going to be. Okay, and then with all those possible values, with their probability in the bar, in the height of the bar, I'm now curious about how, like, where exactly my observed test statistics stand. Okay, if it's right in the middle or like in the bulk of the distribution of the histogram, then we say it's consistent. But if it's not, then we're gonna say it's not consistent, and we're gonna reject the null. Okay, so that's the general framework. And then of course you're going to ask the question whether a value is consistent. How are we going to determine that, right? We talked about, well, you can do a visualization like the histogram, and then that may be sufficient. Okay, sometimes, okay, maybe if not, like say, like I said, if it's in the middle, we will say that it's sufficient. But then what if it's consistent? But what if it's in the tails? Okay, how far in the tail that we're going to make the decision? Then this is where those consistency conventions going to come in. So we're going to talk about them one by one as well. Okay, so, but then just so you know, up to this point, we talk about the 4 general steps of doing hypothesis test. Okay, we come up with the test, come up with the hypothesis. That's the first one. The second step is you're going to compute, you're going to come up with a test statistic. You have to pick a good one, okay, that can help you differentiate between the two. The third is to predict, make the prediction under the null. And then lastly, you're going to make a conclusion of the test. Okay, so if you have time to walk through in your head quickly about what we did in the Alameda County jury selection example, that's exactly what we did. We come up with the two viewpoints, right? We have the null and then we have the alternative. That's how we call them right now, right? And then we're gonna decide a test statistic, right? So in the end, if you remember, we just did the breakout room exercise. We're gonna choose the total variation distance, okay? And then we're going to do a prediction under the null hypothesis for a large number of times. So we're able to get a histogram of the empirical distribution of the statistic under the null, and then we're going to make the decision. Okay, so that's the general flow. And that will be the flow for every hypothesis testing that we're going to do. Okay, so keep that in mind. And we try to revisit that jury selection example. And so hopefully you can make some connections based on what we did already. But now, next, we're going to actually introduce a new problem, okay, how to perform a test for a particular problem, and then we're going to walk the step one by one just to make sure that we know how to do each of the steps in a new setting. Okay, any questions before we move on to that new example? Okay, all right, okay, if not, let me a new one over here. Okay. All right, so immediately after that slide, we're starting this performing a test. Okay, so this is, like I said, a illustration of how a test is being done, a test hypothesis is being done, but then we're introducing a new setup over here. So let's walk through the setup first, and then we're gonna go to the demo to see how we can do it. Okay, so this is, I guess, a problem actually as early as 1972. Okay, people were studying gender discrimination. Okay, in particular, that study had 48 male bank supervisors. Okay, they were each given the same personnel file and asked to judge whether the person should be promoted or not. Okay, so keep in mind here is the same personnel file. Okay, all of the supervisors are male back then, at least in this study. Okay. So keep in mind here that the files were identical, except that half the supervisors had files showing the person was male, and the other half had files showing that the person was female. Okay, so 48, right, in total. So this is saying that 24 of them were male, I guess, applicants, or male, I guess in this case, people to be promoted, right? And then the other 24 are female, okay? Then it was randomly determined which supervisor got the male applicants and which one got the female applicants. Okay, the study showed, okay, out of the 48 files reviewed, 35 were promoted. Okay, the study is designed to test whether females are unfairly discriminated against. Okay, I'm going to show you the breakdown, like out of the 35 promoted, how many were male and how many were female, and that's what we're going to go about doing the test over here. But before we move on, I guess quickly, is this the observational study or the experiment? And can you give reasons why you choose which one you're going to do? Okay. And the second part, I'm going to show it now, the table over here. At the first glance, this is the table, okay, of the breakdown. So we have, like, as you can tell, like 24 male applicants, right? 24 female applicants. So total is 48. That's good. The promoted, okay, 35 in total. So not promoted, 13. The particular breakdown of the gender is that 21 male got promoted, 14 female were not promoted, and that, oh, sorry, let me take it back. 21 out of the 35 are male. Those are the promoted people. And then 14 out of that 35 was female. And the amount of not promoted is 3 and 10. Okay, so these are my questions for you all. So I know this, again, relies on maybe viewing the table before, after I put it into breakout room, but regardless, two parts of the questions here. Okay, is this an observational study or experiment, and why? And second is, based on the table that we're showing over here, do you think there is a relationship between promotion and gender, and why you come up with that decision? Okay, so let me pause. Okay, alrighty. So the questions, okay, two parts. Anybody has any thoughts about whether this is an observational study or experiment, and why? Feel free to speak up. Okay, Sha, please go ahead. Thanks for raising.
Yeah. So we thought that the that it's an observational study because there isn't a specific treatment that is being given to each group. And we thought that there is a relationship. I mean, we can't say it's causation because it's not an experiment, but we can say that there is a relationship between promotion and gender.
And the relationship, I guess you're saying over here, like say the two percentages, for example, the two that I computed are quite different from each other. Is that right?
Yeah.
Okay. All right. Thanks. Everybody's agree about observational study and experiment over here? Okay, I see Juliana says thumbs up. Okay. Everybody? Any doubts? Okay. Interesting. So let me actually reread the question. I thought this is experiment, but let's take one more look over here. Okay. Let's see. So yes, for observational study versus experiment, we always talk about, well, we need to do randomization, if you remember, right? We need to control all of the other factors as much as we can, right? And then just like Xia was pointing out earlier, we need to have this, what we call like a treatment group and the control group, okay? And then, of course, in the usual sense that we're talking about, is always like, say, you give a treatment to the treatment group and then the control group don't receive anything, okay? So let's look at this a little bit more closely over here, okay? I guess it does show, maybe I was going too fast, so it was not highlighted, but it was, I guess, randomly determined, okay, which supervisor got the male applicants and which ones got the female applicants. So there's a randomization, that's what I mean. Like say, we don't know, like each supervisor doesn't know what kind of, like I should say this, each supervisor randomly got selected a particular file. Okay, there's no, like say, I guess for particular, like whether this supervisor has any particular, I don't know, like judgment or anything about things. So I guess that part is probably fine, okay? But let's look at whether other things are being controlled, okay? And let's see. Yeah, thanks, Jeff, for the comment follow-up over there. So yeah, so there's randomization, I guess, of determining who gets to see what, okay? And also, I guess here, the files were identical except for the gender, okay? So when we say this, I guess it's pretty much, you can imagine that the files, they're exactly the same except for the name, okay? Or maybe not even the name. I don't even know about the name. It's really just about the gender, okay? So I think given both, I agree this is probably not like a conventional treatment group and control group that we're used to see, okay? Because it's not clear about like a treatment or a control. What is the treatment, what is not the treatment, right? But what's special here, I guess, is that the two groups of files are indeed selected randomly, okay? As well as there are no any other, like all of the information or I guess other factors are being controlled over here, okay? Except for the gender. Everything is being controlled here. And the problem, as we know, is trying to study gender discrimination, right? So clearly, like if this indeed turns out, if we all agree, but we can keep debating, I'm fine with that as well. If we think this is experiment, then whatever relationship that we're able to determine will tell us certain things about the causality. Okay, if it's not, then we know that it's just going to be a strong association. Okay, so I will keep that for keep it for that now in this style. Like I still think it's more like a experiment just based on what they are trying to solve as well as how the study was designed. Okay, but just in the interest of time, I will just move forward for now, but we'll keep that as open and you can we can all chat on Slack or after class today. I guess for here, I will still tend to think it more of a experiment because of the things that I talked about. And then if we take that for now, okay, we move forward at the first glance over here, the breakdown, just like Xia was pointing out, does tell us there's almost like a 30% difference, right? 30% difference in the percentages of male and female being promoted. So for us, the question becomes, is that 30% due to chance? Meaning that, well, there's no gender discrimination going on. This is just happens that we got a really unlucky sample that the distance, the difference is so huge. Or I guess the alternative hypothesis, right, will be that there is gender discrimination going on. This is not due to chance. There's something going on that we have to test for. Okay, so let's keep going just for the interest of time, but we can always come back about the observational study versus experiment, and we can chat later as well. So here are the two hypotheses I just want to highlight. I just talked about it verbally just now, but the null hypothesis, okay, will be that if we were to randomly select who get promoted, then we have a difference in proportions as large as like 30%. Okay, so meaning that, well, there's no gender discrimination. We would have a difference like that anyway. Or the alternative hypothesis is that no, the observed difference, about 30%, is too large. It's not due to random chance, right? Random chance or randomness is not the only reason for the large difference. It could just be that there is real gender discrimination going on. Okay, so let's work with this too. Okay, and we know that, well, this is only the first step, right? We accomplished the first step of doing hypothesis testing. We finally set up the two hypotheses, okay? And then we still have 3 steps to go. So we're gonna walk through that. Hopefully, yeah, before today's lecture ends, I think we should be able to do it. But I would just highlight here that notice how we set the null and then the alternative, okay? We always set the null that we're able to generate, okay? That we're able to generate data under from. So the null hypothesis, if I frame it in a different way, that there's no gender discrimination, okay? Then if I come back to this data, right? Or maybe even the problem itself, right? If there's no gender discrimination going on at all, then if 30, like out of the 48 being reviewed and 35 were promoted, it's just going to be randomly 35 people, right? Like there shouldn't be any gender like being considered at all. If we think, like I'm just asking, I guess, how are we going to actually go about simulating under the null? Okay, and we can let's pause for 1 minute just to think about it for you all. Like, how am I supposed to, when I get the data, I know it's going to be 48 files in total, right? And I know the gender for each, okay? And of course, in the observed data, I know which ones are being promoted, okay? But then now if we are asked to simulate onto the null, where the null is saying that there's no gender discrimination going on, think about how you're actually going to generate data under it, okay? We have 48 in total, okay? We're going to have a label of whether somebody is promoted or not, okay? And then we also have a label of their gender. Okay? So if you were to do it, what do you think you're going to do? This is a rhetoric question. Don't worry about answering now, but we're going to go to the demo in a second. But I just want to pose this question early on because I think that's actually the hardest part for this problem itself. Okay, like the simulation that we did before is maybe, like say, if you remember, like that 26% Black residents in that county, and then we're trying to generate the number. So we're using the generating from a categorical distribution, right? We have the breakdown, so we're able to generate it. Here, it's slightly more, I think, more challenging and complicated, right? Because we now have to simulate under the null that there's no gender discrimination going on, and then the data that we have, actually, let me just come back to the demo right now here. Okay, let me show you the data and then I guess restate my question one more time. Okay, so the data is coming from this gender promotion CSV file, okay? And it has 2 columns, okay? The gender, so F or M, okay? And then promoted, okay? Whether yes or no, okay? So the first few lines, as you can see, is all of the female being promoted, but then of course there are 48 in total. And let's just double check that the data is telling the same thing as what we are seeing in the table. And this is also a review, okay? So remember, this is a table, a data table, right? We're working with 2 categorical variables, right? So if you want to do any kind of summaries, all right, just bring you back to the group method and the pivot method really quick. Okay, so the group method, and there's also the groups method, if you remember, but let's talk about the group. Okay, the group mostly is only being used for 1 categorical variable at a time, right? We're trying to do summary about it. Say, for example, if I want to know, right, the breakdown of the promoted, okay, what I can do is the data table, right, dot group method, and then in a parenthesis, I put in quote of the name of the label of that column. So here you can see that I have a breakdown, right, 13 and 35. Okay, so this is matching what I was showing you in the table, okay? And of course, we can look at the gender, and we know that it's half and half, right? So if I run this line, it's going to be 24, 24. Okay, so this is, again, the group method being used on the data table and in particular for a categorical variable, so you can do summary about them. Okay, the pivot method, okay, so just to refresh your memory one more time, what if I want to look at cross tabulations of two variables? Okay, so that's what the pivot is doing, okay? And then we have the promoted column and the gender column, okay? So look at what I'm doing over here. I use the pivot method, okay? And I assign it into a pivot table. And then in particular, I want to know the percentages instead of just the counts, right? So that's why I'm doing like dividing each of the row by 24. So let me run this and show you what I did, okay? So if I don't do the pivot table, if I don't do the second line, like doing one extra column, I will only get this 2 by 2 table, right? That's what pivot does. It gives us the breakdown of each of the intersections of the two variables, okay? Like 10, 14, and 3, 21, which is coming from the table in the lecture, okay? But then in particular, remember in the lecture here, I show you this probabilities, right? Like the percentages. So in Python, what you can do is, you see I'm trying to add a new column, right? Called percent, right? And then I'm getting the pivot table itself, the column, the yes column divided by 24, because each row, the total is 24 people, right? For the two different genders. So I'm able to get the two percentages. Okay, 58.3 and then 87.5. Okay, and that's exactly what we're showing. So again, all of this are review really. And then if I want to know the observed difference of the two percentages, I can use the second one minus the first one. Okay, the male minus the female, which goes back to the close to 30% observed difference that we were talking about before we came to the demo. Okay. So hopefully this sounds all familiar, but if not, this is a great review for us for how we're gonna do about summary statistic. Okay, maybe marginally, like looking at one variable at a time, or like bivariate, like two variable at the same time. So for categorical variables, we use group and then pivot. Okay, and then in particular, we're using a pivot here just to show exactly what we want, because we want the observed difference of the percentages. Okay, so that's why we get the pivot and then get the percentage using the with column method. Okay. All right. Now, the most interesting part, at least in my mind, is how am I supposed to simulate the data under the null? Okay, so let me come back to the data really quick. This is the data table. Okay, we have a column of gender. Okay, we have a column of promoted. Okay, so maybe let me just like put you in breakout rooms for 2 minutes and then come back. Like, how do you think what you're going to do if I'm trying to simulate a sample under the null hypothesis, where the null hypothesis is saying that there's no gender discrimination going on? Okay. I'm showing you the data table. One column is gender, the other one is promoted. How are you going to simulate a new sample under the null hypothesis? Okay, so this again, like I said, is probably the most challenging part, but I still think it's good to give you the chance to talk about it before I show you in the demo of what to do. But as you will see, once you see it once, I'm pretty sure, like, for this type of challenge in the future, you're gonna do something similar. Okay. Resume recording. Okay. So again, in the interest of time, I probably will just go ahead of doing the demo. But just to remind you, we're curious about how we can do a sampling, right, of under the null, meaning that we want to generate a new data set that the promoted column is randomly selected for each record. Okay, so that's what the gist is, right? Like each record we know about the gender label, but then we know that under the null hypothesis is saying that there is no gender discrimination, right? So the promoted, whether somebody's promoted or not, should not be related to gender. That's what really that null hypothesis is. So putting into our practice of doing like a Python programming over here, pretty much one way we can do it, which is the one I'm going to do the demo for, is that, well, if the promoted column should not be related at all, right, about the gender, then that is pretty much the same saying that I know I have 35 out of 48 are promoted, right? So I have 35 yeses and then 13 no's in this column. Okay, so what we can do is that, well, I can do a sampling without replacement, right, of the entire column of promoted. And that later you will see that we call it like shuffling. Okay, we're shuffling the labels of yeses and nos of the promoted, and then we just put a new ordering coming up. Okay, so, and then under the assumption that the null is true, meaning that there's no really relationship. So each time I generate a new promoted label, I'm just like randomly shuffling the labels of yeses and nos in the promoted column. Okay, so again, you will see in action how we can do it. And once you see it, it's not going to be something too challenging anymore, I'm sure. But I think it's very important to talk through why we do that. Okay, the reason why is that we know the null hypothesis tells us there is no gender discrimination. So for us to like implement that in practice, what that means is that, well, regardless of the gender column, right? If I'm only looking at the promoted column, I will just have the 35 yeses and 13 nos randomly shuffled around. Okay, shuffled around meaning that I don't like, I shouldn't care about the gender for any record anyway. Like it could be any kind of arrangement of the promoted column. Let's put that way. Okay, and to do that in Python, we're going to use the sample method. Okay, actually we have seen this method before. Okay, but in particular, what I'm going to highlight here, we're going to do sample without replacement. Oh, sorry, let me put it back, with replacement. Okay, meaning that we're able to remember, like we have 13 yeses, right? Sorry, 35 yeses and 13 nos over here. So we're going to do a sample like that with replacement, and then we're going to get the promoted column. So let me do this shuffled, what we call the shuffled labels. Okay, so this whole line, what this does is that we're doing a sample with replacement based on the 35 versus 13 breakdown. Okay, and then we're able to get it also the promoted column. So if you look at over here, if you do the count, you're going to get 35 yeses and 13 nos. But what this is doing, because we are adding the sampling, right, the sample method over here, meaning that we're performing a new arrangement, okay, of this promoted column. Okay, right now it's still in an array, but then of course, as we know now, we're going to put it back, right, using the with column method, so we can create a new table, what we call the shuffle table. Okay, so the shuffle table gonna have the same, exactly same column of the gender as before. Okay, we don't touch it, but then we add a new column based on the shuffled labels. Okay, so let me walk you through one more time. The table, the gender promotion table was the original data, right? We have the column of gender, we have the promoted column. Okay, what we're doing now with the shuffled table, okay, is that we're gonna keep the gender column unchanged. Okay, but we're randomly shuffling the labels of the promoted column. Okay, we're still going to have 35 yeses and then 10 nos, but now we're shuffling it, right? Meaning that, well, I don't care about the gender at all. I just want to look at a new like a new arrangement which is randomly generated, right? And then from there, now you can imagine, right? Now we can do the pivot again, right? We can do the summary, and then let's look at after one simulation. You can see that the percentage of female in this simulation is 67-ish%, right? And then the percentage of male is like 80%. If I look at the difference, is what is like 12.5%. Okay, so this process is that we're using the sample method. Okay, in particular, we're shuffling the labels, right? The actual, I guess the each of the observations for the promoted column. Okay, and then we're shuffling it so we can have a new arrangement that is independent of the label of gender. Okay, and then once we get a new shuffled data table, right, we do the same thing as what we did with the observed table, right? We get the pivot of promoted and gender, and then we take the percentage difference, and then we can see that in this case we get 12.5%. Okay. And of course, the next step, right? So this is like determine the statistic, right? And then simulate the statistic, okay, with one sample. Now we put everything in a function. In the interest of time, I won't walk through like each line of the function, but each line, as you can see, is like just coming, we're just like condensing all of the little steps that we have done so far. But we call this whole thing as random sample percent difference, okay? Meaning that, well, I'm gonna create my shuffle labels, and then I will get my shuffle table, and then from there I'm going to do the pivot, and then I could do the summary, so I can take the like the distance or like the difference between the two percentages after one simulation. Okay, so I'm going to run that, And then this is going to take some time to run. So let me just set it to run. I run this function, right? And now I'm going to run the function for 10,000 times. Okay, so again, what I'm doing is that I'm simulating the statistic, which is the percentage difference of male and female get promoted. I'm simulating that statistic under the null hypothesis for 10,000 times. Okay, so this, if I come back to what we were talking about, the different procedures here, right? If I come back here, is prediction under the null, right? I did the prediction, and like what we're saying over here, we're gonna get a histogram, right? And we will, let me show you earlier, like over here. Okay, so this is the histogram. Okay, this is the histogram of the random sample difference. If I'm sampling the difference, which is the statistic, right, under the null hypothesis for 10,000 times. Okay, make sense? Make sense? Yeah, so this is the histogram that we're talking about. And let me just see. Yeah, it's really hard to read. Sorry about, let me actually add the size maybe to 80. Let me run it one more time. It's still hard to see, but anyway, what I'm trying to show is that this little red dot, sorry about it. Maybe I should, let me put, anyway, this red dot over here, that's the observed difference of 30%. Okay. And what I'm showing you here is we know that the histogram is telling us, right, the empirical distribution of the statistic under the null, right? And I did it for 10,000 times. And then we are saying that in order to make the decision, right, you're gonna compare the observed test statistic, which is about 30%, right? And then we're gonna compare it against the histogram to show how, whether they're consistent or not. Okay. One quick way, well, visually, this is actually a hard call, I would say. That, well, whether this is extreme or not, like if it's not in the histogram at all, then we know that it's so extreme that it's probably going to be inconsistent. If it's more closer to the center, we're probably going to say it's consistent, right? But it's somewhere in the tail that is hard to tell, which we're going to carry on Thursday. But let me just show you really quick, which is actually the definition of p-value, which we're going to come back on Thursday as well, is that the p-value is computing in our setting is that how many of the sample differences that I'm able to compute, right, 10,000, out of the 10,000 ones, how many are as extreme as the one that I have observed, okay? And then I want to know the percentage. So you see what am I coding here? The sample difference is greater or equal to the observed difference, and then I'm taking the sum of, so these are binary, right, Boolean, right? And then I take the sum divided by the number of simulations I've done. So this gives me a probability, which is actually a p-value. Okay, so p-value, as you will know, sorry, I didn't manage to cover that, but on Thursday when we come back, and I hope we'll be able to address the previous questions a little bit more as well, is that how are we going to make the decision, as well as, well, what does it really mean to have like p-hacking, and then why people are so, like, I guess why, in the first place, why people care so much about p-value in the first place, and then how they're making the decisions. Okay, so I'm just going to end here. But the demo is available for you to view, so feel free to check it out. Like I said, especially the shuffling step is probably new to most of us, okay? Especially like why we're doing it, how we're going to do it in Python. So I highly recommend you to revisit this after the class before Thursday, because on Thursday, I guess we're just gonna pick it up from where we left and just going to continue talking about the other terminologies in the course. Okay, but in the meantime, take a look at what we had in the demo. So to run it by yourself, I think it's always a good learning and then good reinforcing of why we're doing this and how things are done. Okay. All right, y'all take care. I will stay over if anybody has any more questions, but if not, I will see you later this week.
Thank you.
All right,
bye.
Thank you all.
All right. All right, let's get started. So before I dive in and talk about today's lecture, I want to announce that, and I think I sent this out on the Slack announce channel, that we have the template for our final project that's going to be released. So we're not going to do a final in this class, like a kind of written exam. We're going to do a final project. And so basically this notebook here is where you'll do your final project. And so if you notice, the notebook is kind of, it will allow you to kind of will guide you through the final project. And we want this to be kind of as open-ended as possible. And so nominally this course came about because of this HHMI grant that we got, this Grand Challenges for diversity inclusion in pedagogy, centered around this theme of climate change. And so this course is a cluster of about 10 courses throughout the college with the topic of climate change. And so we've kind of curated some data sources for you that we've put on Moodle. But we also understand that, you know, the world has changed a lot since we kind of put this proposal together. And we are living in the midst of a, you know, COVID-19 pandemic. And, you know, I think I want to kind of nod to the fact that some of you may want to, I mean, COVID-19 has impacted all of us in many different ways. Some of us, you know, greatly more than others. And so, you know, I want to, and I don't know if encourage is the right word, but if you're inclined to do a project about COVID-19 in kind of lieu of a climate change project, we're supportive of that. It's really kind of up to you whether you want to do that. I kind of curated a couple of data sources that have been kind of tracking the pandemic since the beginning. And so if you'd rather do some impact, you know, some project related to COVID-19, we're supportive of that from there, but don't feel obligated to do that. Many of you may be COVID-19 burnt out, and the last thing you want to do is kind of dive down and study that, and that is perfectly okay as well. You know, let's stay the course and kind of do the project on climate change, but I want to be supportive of that if that's something that you're kind of personally inclined to do. And so the good news is that the template will kind of guide you through, regardless of what data set that you pick, will guide you through kind of approaching this as a data scientist would, about, you know, looking at the data, visualizing the data, cleaning up the data, and asking some pointed questions about the data and doing a little bit of analysis. And so we want to kind of throw this template out just to kind of know what, you know, what we're kind of expecting. And so kind of the end product, so the kind of the immediate thing, and the reason why I'm mentioning this now today is kind of your first task is to form your team. So there's 21 of us in the class, and so we're going to do groups of 3. And so we'll have like 7 groups. And so you know, so what we want to do is sooner than rather than later establish what those teams are, what those groups are, and we're happy for you guys to pick the groups yourself. We can also facilitate, you know, doing some matchmaking as well, or if you just want to leave it up to random fate, we will, everyone that, you know, doesn't have a group by Sunday, we'll randomly assign you to your group. So either way, kind of by the end of Sunday, we'll have those groups. And so once we have those groups together, those teams, what I'll do is I'll create a new Jupyter Hub login for that team. And so, you know, really we're trying to solve the issue here of how do you share data across the different accounts, and how do you kind of edit the notebook. And so I think a reasonable solution is that we'll have a team account. So I'll have a password, you know, all the members of the group will have that password, and that will be kind of the joint place where you can work on your notebook together. And you can have multiple people logged in at the same time for your groups. And so that's a good way that any data that your group is using, it's there, and it's going to be easy to share, as opposed to if you're working in your individual accounts. How do you update Jupyter notebooks? How do you update data? All of that. So that's what we'll do. But we need your team. You know, we need your team, the members of your team, so I can set up those. And then just as kind of like a workflow. If multiple people are editing the same Jupyter notebook at the same time, you could run into conflicts. it actually handles it, relatively well. But the thing that I would recommend doing is once you've had your groups, make a copy of the notebook. And so you can have kind of the one copy, the final project, notebook, that's kind of the official version. And what I would recommend doing is that when you're doing work on a particular aspect of it, create a copy of the notebook, and then you can work individually. So, create a copy of your notebook, copy of the notebook, like with your name, with your login, like associated with it. And then you can work individually on your own project. You can kind of use that as kind of like the scratch space. And then when you kind of get everything working, then you can kind of copy over those cells into the official notebook from there. And that way, that will kind of avoid conflicts, and you can kind of coordinate, someone who's doing kind of the final edits for that. So that's kind of the workflow that I would recommend for that. And so we've kind of outlined the parts that you want, and we've kind of put pretty clearly how much those points are worth. And then instead of, so once you've turned in kind of your notebook, we're going to ask that you do a short, 5 to 7 minute video presentation of your project. And you can do that, you can record that, using Zoom. We did that last time we offered the course, and I think it worked out pretty well. And it's a good way to kind of present your work and thinking about visualizing the data and practice, giving yourself practice giving a talk and condensing it down into 5 or 7 minutes from there. Any questions? Any questions about this? And we'll have time to talk about this in lab. And as a matter of fact, if you're unsure about who you want to work on the group, use lab time, either in person or remote. You can use that time to meet some of your fellow classmates and talk to your fellow classmates, and let us know what groups you'll be working in there. So that's the big one. That's the big one. Find your group, and then Professor Hu and I are happy to talk about project ideas, different ways of kind of approaching the data, especially if you're going to kind of do a COVID-19 project. We're more than happy to discuss kind of the nuts and bolts of the project. But basically, the goal here is that you're just going to take this notebook and you answer all of the questions, and have the nice thing about Jupyter Notebook is it really is self-documenting, right? The way I like to think of Jupyter Notebook as it's an electronic, experimental library notebook. Hence the name Jupyter Notebook, right? That when you run experiments, you can put your notes on the experiments right in the code itself. So it's basically self-documenting code from there. And so anyway, I wanted to let you kind of know kind of what's coming up there. And so then after you form your teams, the first checkpoint here is a couple weeks from now. So Sunday, May 2nd. And really what we're asking you to do at this point is to just really kind of think about the data sources that you're going to use and visualize them. And think about what question you're going to want to ask. So we're not really asking for any types of in-depth analysis or inference at this point. We're really just asking that you've kind of picked a data source and have a good idea of the questions you're going to be wanting to ask about the data. And like I said, we'll guide you through this, and we'll definitely set aside some lab period, sometimes in lab period to talk about this. Either remotely or in person from there. Okay. Yeah, so I think that's all I want to say about the project for now. Any questions before I kind of move on to our topics for today? All right, excellent. All right, I want to pick up where we left off last time. And I want to talk about this idea of, so now that we kind of have this way of running these experiments and generating these histograms and comparing these simulations to our observed value, now we want to answer the question, does our observation, have statistical significance? And so I want to put a kind of precise definition about what does that mean. And so when we started looking at the distributions of our simulations, we see that a lot of these distributions, depending on the statistic we have, they all kind of have this tail, right? So you can see in kind of this idea of this random count, we actually kind of have two tails on either side of the distribution. And then metrics typically kind of dealing with distance, because we're taking the absolute value to calculate the distance. We usually see kind of these one-sided tail distributions. Like if we're looking at the diagram in the upper right-hand corner, right? If you remember, this was the Mendel experiment for the peas, right? And we calculated the distance from 75 because our model was 75% of the flowers were going to be purple. And so you can see that, the tail goes off into the right. And then when we looked at the jury pool selections, again, we're using another distance metric, this idea of total variation distance, this TVD. And then, as we have the tail kind of going off into the right. And so we can use this to talk about whether our hypothesis is consistent, the observed data is consistent or inconsistent with our that our observation is consistent or inconsistent with our experiments here. And so to be kind of precise about the terminology, inconsistent means that the test statistic in the tail of the empirical distribution, right? So that is our simulation. That's the simulation that we ran under the null hypothesis, right? So the thing that we have observed, the test statistic that we observed is in the tail. It is kind of an outlier from there. And when that happens, we say that the test statistic is inconsistent under the null hypothesis. And so what does that mean to be in the tail? Well, there's a couple of kind of conventions that are in use. And one of them is that we look at the tail and we kind of put a marker where the area of the tail is less than 5%. So if you remember, our histogram is going to sum up a total area of 1. So if we look at the part of the tail that is less than 5%, that's our first convention. So that cutoff is 5%. And if we say if it falls within that 95, that observation falls within that 95%, we say that the result is statistically significant. The second convention, kind of the same idea about looking at the tail, but we just have a sharper cutoff, a more strict cutoff. We have that cutoff at 1%. And then we would say, if that is the case, we would say that the result is highly statistically significant, which means it is 99%, not due to chance from there. Okay. And so we can look at this. We can look at a couple of examples. And so if you remember from the simulation that we ran from last lecture on workplace gender discrimination. And so this is the result that we got. This was the distribution that we got. And if you look at the kind of the two lines, we can draw one at 5%, which comes around a 0.2 difference. And we can also look at the 1%. And you can see in the 1%, the tail, the area underneath here, on the other side of that is going to be, is going to be smaller for the 1%. Okay. And so we can use this now to have a formal definition of our p-value. And so formally, what we kind of colloquially call the p-value is, its formal name is observed significance level. And so what does that mean? Kind of precisely putting it, the p-value is the chance using the null hypothesis that the tested statistic, the thing we observed, is equal to the value that was observed in the data, or is even further in the direction of the alternative. And so in the gender discrimination, the alternative is off to the right from there. Okay, and so this p-value, this line, is basically the percentage of that is going to be due to chance for there. So now going back to that demo that we looked at last time, how would we calculate the p-value in this gender discrimination example? And so let's refresh our memory what that demo looked like. And so if we look down here, this is the the result of running our experiment, running our simulation. And if you can see, so here's the histogram distribution that we got through our sampling. And then down here, it's a little hard to see, but where my cursor is, you can see that was our observed statistic. That was our observed statistic. And so let's take a moment before we kind of look at the demo. How would we determine whether it falls under this 5%, this p-value there? So let's take a moment. Let's take a moment to think about that. I'm going to send you off into the breakout rooms. Recording. Okay, so let's talk about how we actually can calculate the p-values here. And so going back, having a look at our demo, we can see, so when we did our simulation, we ran it, we computed the statistic 10,000 times, 10,000 times, and we used kind of this accumulator pattern, and we stored the results of our simulation each time we ran it. We stored it in this sample difference array. And so the sample difference array, this is what we used to make this histogram here of all of our, to get our empirical distribution from there. And so we know that we have this value, which we've shown on here. And so now the question is, how do we calculate that p-value? How do we actually get that percentage? And the easiest way to do that is, what we can do is, so we have our difference. So I'm looking down, if we're looking at this cell down here from here. So here's our array. So here's our array of all of the empirical observation that we've done. So those are all the values that we got by running the simulation. And so what we want to do is we can compare all of those simulations to our observed difference, right? So this is the statistic that we computed from the actual real life experiment that they did. And so what we're going to do here is so sample difference is an array, and this is a constant, this is some value, and we can use the greater than or equal to test. So what that's going to do is that this is going to return an array. This is going to return an array, one for every element in our array, for each of the individual tests. So it's going to do this test. It's going to do this test for every item in this array, and it's going to return a new array that that has true or false. So it's going to be an array of true or false, whether you were greater than or less than to this observed statistic. Okay, and we know if we look at a sample difference that's greater than the observed statistic, that's going to be over to the right. Okay, and so then what we can do is we can take the sum of that array of true and false. And the way that works in Python, it will count anything that was true as a 1 and anything that's false as a 0. So that sum is going to tell us the number of this simulation, the number of elements in that array that were greater than or equal to the observed value. It's going to give us the count. It's going to give us the count of all of everything on the right side of the histogram there from our observed. Okay, but what we don't want the count, we want the percentage. So we need to divide that by the total number of simulations that we ran. And in this case, that was 10,000. And if we run this, we get the value 0.02. And so turning that into a percentage, that's about basically 2.7% from there. Okay, and so that's our p-value. That's our p-value. One little kind of programming note so this value of 1,000, like where did we get that? Well, that was because we knew we ran 10,000 simulations. How did we know that we ran 10,000 simulations? Well, we can go up to the cell where we ran the experiment. This is like a hard-coded number. In kind of computer science, we call those kind of magic values, that they're just kind of hard-coded in there. And you don't necessarily need to do that. This is the right thing to do, but one of the things that we can do is, remember, sample difference is the array that we're pulling from. And so instead of hard coding 10,000 in here, one of the things that we can do is we can just do the length of sample difference. And this will compute the correct statistic. Again, if I run this cell again, I'll get the exact same answer, 2.67. This will compute the correct answer no matter how many simulations that we ran. So if we went back, so the problem with kind of hard coding this number here is that if you go back and say, oh, what would happen if I ran this thing 20,000 times, and you forget that you hard coded this value of 10,000 in here, you have to remember to change it in both places. Okay, so that's just kind of a good programming tip through there. But as I said, we kind of get the exact same answer. Okay, so that's the p-value. That is the percentage that we got. So how would we calculate the number of observations? Excuse me, for 5%. Well, again, we have our array of observations, and so taking note that 5% of 10,000 is 500. Well, to kind of find the actual cutoff point at 5%. We can just basically say, we can look at the value at that item, the 95th hundredth item in that list, provided that we sorted the table, right? So here we are, and again, right, the way we've defined our statistic, the tail is going outwards and to the right, and so larger numbers, numbers larger than our observation, are going on the outside of that. And so it's important that we take our table of differences, is that we sort it first. So then we're going to put them in order, and then we're taking the column from there. And then if we take the 95th, the 9,500th item from there, that is the actual value. That is the actual value of the 5% from there. Okay. So if we take a look, now that we have that value, that 0.2 value, now that we have a 0.2 value, we can display that on the histogram from there and see where we fall, right? So if you look at our observed value up here, you can see that it kind of falls outside of that 5%. And so we would say that for this experiment, that the result was statistically significant, right? That's from there. But remember, we talked about kind of these two different points that we talked about. We talked about this 5% point, and then we talked about this 1% point. And so if we wanted to see where we fall within the 1% point, we can redo the experiment the calculation that we did up above. But 1% of 10,000 is 100. So we can look at the value of that point, and that comes down to the difference of 0.29. And so if we look at that in the same plot down here, you can see that while it's greater than 5%, it is less than, our observed value is less than 1%. From there. So this is we kind of pick this set of data in this experiment because it falls right in between that 1% and that 5%. And so we would say that the result is statistically significant, but as we put it here in our terminology, it is not highly statistically significant from there. Okay, any questions about that?